So let's take one more example. Suppose I have some mass of water at some temperature T1 and an equal mass of water at temperature T2. One is hot and one is cold. I put them together. What will happen? We believe you will then get this big mass all at some common temperature T star, which is T1 plus T2 over 2. This is just by symmetry. It's equal mass, equal specific heat. Where will they meet? They will meet halfway. They will meet here. Energy is, of course, conserved, and that's how we determine, in fact, where they will meet. But look at the entropy. What happens to the entropy change? Then the delta S total will be m, specific heat is 1, then delta T over T, starting from T1 to T star for one thing, and dt over T from T2 to T star for the other one. You understand that? They both meet at T star. Upper limit is T star, lower one is T1 for one and T2 for the other. So the change in entropy becomes m log T star square over T1, T2. Now, to prove it, we will do what he just said. If you want to prove this is positive, you want to show that the fellow inside the logarithm is bigger than 1. So I'm asking, is T1 plus T2 square over 4 bigger than T1, T2? Or I'm saying, is T1 plus T2 squared bigger than 4T1, T2? If you rearrange this, you can show the left-hand side becomes T1 minus T2 squared. That's, of course, a positive number. So when hot and cold meet and reach lukewarm, entropy of the universe has gone up. It follows, therefore, if lukewarm spontaneously separated into hot and cold, the entropy would go down, and that's why that doesn't happen. That's why if you leave a jar of water at one temperature, it doesn't spontaneously separate into a part on top, which is cold, and a part on bottom, which is hot. Such a separation would not violate anything. Okay? It would not violate the law of conservation of energy, but it will violate the law that entropy has to always go up. So one way is allowed, another way is not allowed. So you see over and over again that anything that's allowed is in the direction of increasing entropy. Anything that's forbidden is in the direction of decreasing entropy. But who is this entropy? What does it mean? Well, that we have not understood at all from any of these calculations, because dq over t doesn't speak to us the way du or dq or pdv does. So the last part of what I'm going to do is going to explain to you what is the microscopic basis of entropy. For that, I'm going to consider the following process. I take a gas and I put it in a room, in a box, where there's a partition halfway. The molecules are stuck in the left side. Gas has reached equilibrium and it's done what it can, which is to spread out over this volume. Now I suddenly remove the partition, just rip it out. So let's follow this gas. Initially, it is a point here. Then there is a period when it goes off the radar, because I told you, when you suddenly remove the wall, the gas is not in a state of equilibrium. It doesn't even have a well-defined pressure. The minute you remove the wall, pressure is something here, pressure is 0 in the vacuum here. So you've got to wait a bit. So gas has gone off the radar. We cannot talk about what's happening. Then if you wait long enough, I get a gas that looks like this after some seconds or whatever milliseconds. That is, again, gas in equilibrium. It's got a certain state. I can call it 2. What is the entropy change now? That's what I want to ask. What's the change in entropy here? Because I know that this is allowed, that is forbidden. So I want to ask, did the entropy go up? Now, how do we do the entropy calculation? Here's a wrong way to do the calculation. You go back and say delta S is delta Q over T. But this whole box, I forgot to mention, I'm sorry. This whole box is thermally isolated. It's not in contact with anything. I just ripped out the partition in the middle. That's it. So you might say, well, if it's thermally isolated, delta Q is 0. So you can divide by T. You can do what you want. So this entropy change is 0. But that is a wrong argument. Can you think about why that's not the way to do the entropy change, or why that's the wrong analysis? Wait. In fact, here is the interesting thing. what's going to be the temperature difference between before and after? Which is going to be hotter or cooler? Even when I remove this piston here, there is no pressure pushing this gas back. You understand that? Doesn't do any work. Doesn't take any heat. So what does that mean? In the end, when you settle down, what can you conclude then? No heat input, no work done. So what does that mean in terms of temperature? Same, because the internal energy cannot change, because delta Q is 0, work done is 0. So in fact, this is a surprise. This gas, when it expands, will be at the same temperature. Now you guys are thinking of the computer air, where if you let it expand, it cools down, because that is expanding against the atmospheric pressure. This gas is expanding into a complete vacuum. It's got no piston to push against, nothing from outside pushing. So these 2 points are at the same temperature. So the correct answer, maybe you didn't catch on, but I will tell you the correct answer is there is an entropy increase in this problem, because the final state definitely has a well-defined entropy you can calculate, because it's an equilibrium state. Initial one has a well-defined entropy. In between stages here are not on the PV diagram, because they were not equilibrium states. So in this experiment, the way to calculate the entropy change is not to do delta Q over T as it happened in this experiment. What you really want to say is, my gas was here in the beginning, my gas is there in the end. Both are states of equilibrium, both have well-defined temperature, and I can find the entropy change in going from here to here by any process I want. As long as that process keeps the system near equilibrium, so I can follow dot by dot where I'm moving and add the delta Q over T. The correct rule for entropy changes is delta Q over T computed on a path in which the system never strays from equilibrium. Now, your system strayed from equilibrium all the time, but we're not interested in how it got from here to here. We are saying, what's the entropy here and what's the entropy here? Since it's at the same temperature, I know one way to go from there to there is to follow the isotherm, because that will connect the 2 points in this particular problem. Then I know the entropy change is S2 minus S1 is NR log V2 over V1. The free expansion of a gas into a vacuum takes it from one equilibrium state called 1 to another equilibrium state called 2. In the actual expansion, the system went through states which cannot be even shown in the PV diagram. They were not equilibrium states. It didn't have well-defined pressure, didn't have well-defined temperature. How do you define a temperature when half the box is empty? Doesn't have, you cannot call it the temperature of the gas. So what do you mean by delta Q over T? There is no T. Only when it settles down, there is a T. Every settled down equilibrium state has a well-defined entropy. What we're trying to do is to compute that difference. The way to compute the difference is to forget about what actually happened and instead do the following. Take the gas like that and turn it this way, if you like, just for convenience. Put a piston there at the halfway point. Put some weights on it so that the pressure equals the pressure inside. And slowly remove little by little and keeping it on a reservoir at temperature T1, which is the temperature at which all of this happened, or at some temperature T. As you remove the grain of sand, what happens is the gas gets some energy, that's a delta Q over T. The reservoir loses some heat. In fact, the reservoir loses the same amount of heat, delta Q, at the same temperature T. So in fact, what happens in this process is the entropy of the universe does not change at all. The entropy gain of the gas is the entropy loss of the reservoir. But I use this as a device for finding the entropy gain of the gas in the other process. So this is the part that's absolutely central to this whole argument how entropy is calculated. In a real spontaneous expansion of a gas, where there was no reservoir, no nothing, we just broke the partition and expanded, there is a change in entropy. That's an irreversible process. But to find the change in entropy in this problem, since 1 and 2 have well-defined entropies, we can find the change between 1 and 2 by going to a different experiment in which it was brought from 1 to 2, not in this crazy irreversible way, but by putting it in contact with the heat bath at that temperature T, removing grain after grain, never straying far from equilibrium. That's when we find this change. So you replace the dotted line, where you cannot compute anything, by a solid line where you can, but since the change in entropy between 1 and 2 doesn't depend on how you got there, that's the answer. But this process, where you can actually see it, is a one in which delta S of the universe is actually a 0. Why? Because you're putting in contact with the reservoir at the same temperature. So delta Q over T for the gas and delta Q over T for the reservoir exactly cancel because they're at the same temperature, and delta Q for one is minus delta Q for the other. So don't confuse the two processes. One is a reversible process in which a gas is slowly allowed to expand from the initial state to the final state by removing grain after grain of some externally applied pressure in a process where the entropy of the universe doesn't change. Gas and reservoir change by equal amounts. But the punchline is, I don't care what happens to the reservoir. I want to know how much the gas gained, because that is the gain I need to find S2 minus S1 for this process. So this is how we always find entropy change. In real life, processes happen in a way in which the entropy of the universe goes up. Because take this box. In the real experiment, remember there was no reservoir. There's only the box of gas. It expanded, its entropy went up, so entropy of the universe actually went up. That's why it's allowed.